in this overview. So at the end of this presentation,
Right. Okay.
I give a little bit of insight what we are doing here, or what we started here in Zurich.
So I can already tell that I'm going to ask you to speak up. So it's just like a regular talk in which you kind of have to shout at people, I think. A little bit. Not too much.
Okay. How is the audio? Well, I had some difficulties with the audio, so
it's fine now. It's fine.
Okay.
Yeah.
Okay.
If I can't hear you, maybe I'll make some reaction.
Okay.
Like,
and it might also be the case that the connection will be lost or something.
Yes.
Like that, because I'm doing this on a very old Surface Pro, which is 7 years old.
Right.
And I always hope that at least it will.
Nothing will go wrong. I'm completely sure.
If the connection goes, I'll get a panicked email from me. So.
Okay. Yeah. Yeah. Not that I continue talking and then I'm reaching the end and then you only got half of the presentation.
Yeah.
So in our experience, it usually happens that the computer goes out just as your talk is really getting the high point of interest, right? That's when it'll go. And we're recording. Excellent. Thank you.
Yeah, no problem.
Continue. Simon, when do we usually start? Is it like we usually wait some minutes after 2?
So I usually get about 2 minutes after the slot, really, just to make sure.
Right.
We'll trick it in, but we don't track it out too much.
The if it's physical, it never gets started before like 7, maybe 10.
No.
In France, they routinely would not start until 25 minutes after the appointed time, and I was out of my mind. I didn't understand how that's possible.
That would give me some anxiety, I think, trying to manage that.
Yeah.
In Austria, it's 15 minutes, so
but it actually starts.
Yeah, after 15 minutes it starts. So you were right. It starts at 2, but when it's an invitation from the university, it's 2:15.
Right. That's kind of like movies. Movies are that way, right? You get to it at a time, and then there's some slush period where they want you to buy refreshments.
Oh, maybe we should do trailers.
Yeah. Well, we could do announcements. That might be reasonable. Go around and do announcements. In America, meetings start on time. They start on time, and it's weird if you're not on time. It's just
have like a slideshow with some gentle music, just
welcoming us to Odeon.
Yeah.
Welcome Christina as well.
Hi. Hello.
Hi.
Have we rescheduled you?
I don't think so, but it's been so weird lately that I think we didn't.
I don't think I've sent an email yet, but I'm currently destroying my house, so.
Are you moving today? What's the story?
Moving on the weekend.
Oh my God.
So currently I'm trying to destroy all my furnishings and get rid of them, unpack everything.
Some people are at the Risk Institute address. They're in the wrong meeting. I don't actually know how to tell them otherwise, now that I'm on here.
What do you mean that the wrong meeting?
Well, I've gotten an email from Zoom that says, Elfrida, but you're in the right meeting, Elfrida, aren't you? And Marco. Forward.
Yeah, Nick posted a link on Slack, so that's why I found it. Otherwise, I didn't know where to look for the link.
Let's see if we can get it from...
Information on my email I used to get in was correct, so I'm not sure.
Do you know how I can get the address conveniently? I guess
there's one on the email that went out. which I use to get in.
Just means Marco. Both Marcos.
Have the trailers started yet? I'll go warm up the popcorn.
This is the ambience.
Does anybody have any announcements they should make to a big group?
I guess you would be the person for that, Scott, no?
I'm sorry?
I guess you would be the one to make any announcements if there's anyone.
Yeah, well, no, I think it's everybody, but it looks like we don't have any announcements. So, Simon, do you want to make an introduction, or Jürgen? Does everyone know Jürgen?
Otherwise, I will give a quick introduction about myself in the next 2 or 3 slides.
Right. Well, you all know that when we lost Ivan Au, and then John Mottershead, and then Alex Diaz, and then Edo Patelli, Jürgen has come in to fill those shoes. So good luck with that, Jürgen. So Simon?
Yes, so a quick introduction. Dr. Jürgen Hackl is a lecturer at the University of Liverpool and a member of the Data Analytics Group at the University of Zurich. His research interests lie in complex urban systems and spans both computational modeling and network science. Much of his work has been on improving the understanding, design, and performance of complex independent infrastructure systems affected by natural hazards. So Jürgen, want to take it away?
Yeah, thank you very much for the introduction. Also, thank you very much for the opportunity to give a talk here. Actually, it was scheduled at the beginning or mid of March, I guess, but unfortunately, due to the coronavirus, now we have it remotely and a little bit later. Yeah, so this talk is more or less a quick overview of past research I have done, but also my current research interests and ongoing projects. So it will be at more at a higher level talk. And yeah, if there are any questions pop up, please let me know. I think the group size is big enough so that we can interrupt and have questions. Okay, today the talk would be about complex infrastructure systems and how we can manage those systems regarding risk and resilience. Also at the title slide, it already shows my research interests. So it's going from, let's see if this is working. It's going from the real world system to engineering modeling, where we model hazards, and then going a little bit further into more mathematical stuff and trying out new ideas and new ways how we actually can model our infrastructure systems and how we can analyze those systems. And this will be more or less the outline of my talk. I will start more first with the engineering models, and then towards the end, I will reach more mathematical model. Okay, as I mentioned before, I would like to start with a very brief introduction of myself about my past history. So I did my first master in civil engineering at the TU Graz with focus on construction management. And then I did a second master joint master at NTNU with the focus on computational modeling. And yeah. Also, during this period, I started to fall in love with Emacs and Linux, which I carried on throughout the whole project. And you will see some hints about this also throughout this presentation. Maybe one quick thing. So this presentation was purely done in TickZ and LaTeX, if people know this. So yeah, it's one hobby of mine. So then I started at ETH doing my PhD. And there I started to work more on infrastructure systems, which also resulted that together with my former supervisor and another colleague of mine, we created a small company who is giving guidance infrastructure engineers how to manage and optimize their infrastructure systems. Also at this time, I started to code on cloud simulation, a computational platform, which I will introduce later. So after my PhD, I quickly joined the University of Zurich. They are the computer science department under the supervision of Ingo Scholtes, and there we are working on machine learning techniques for networks. Also, I will explain this a little bit later in my talk. So the main point what I'm doing there is working on PathPy, which is a Python library to do exactly this type of machine learning. And then recently, at the beginning of this year, I joined the University of Liverpool. And yeah, that's where I'm right now. And you see in this slide that I guess the paths are open now and here to explore new ideas. And hopefully also I can collaborate with some of you guys. Okay, that was more or less a quick introduction about my background. Now a quick introduction about my research interests, and I joined science not only because I like programming, but also I like to, at least in small steps, help our society. And where I see my research more or less in the bigger picture is in these 17 Sustainable Development Goals from the United Nations. Where I can contribute with my knowledge would be in infrastructure, sustainable cities, so urban development, and climate action regarding natural hazards. In more particular, my research interest is split up into three main parts. First one would be computational modeling and large scale simulations on high performance clusters. The second one is a little bit more mathematically, which is network analytic methods for complex infrastructure systems, which can be represented as networks. And then the last pillar is a long-term decision-making under uncertainty. So how can we use the first two pillars more or less to make better informed decisions? Today, in today's talk, I will briefly talk about all these three pillars, but mainly focusing on the first one and a little bit on the second one, and the last one I only mentioned briefly in a couple of slides. Okay, when I talk about infrastructure systems, I think most people know from a civil engineering background that I'm talking about transportation, power, communication networks, railway networks. So that's when I talk in this presentation about complex infrastructure systems, I mainly mean those networks. Why they are complex? Because there are multiple different parts. They have all act with each other. For instance, in this railway network, we not only have the physical tracks, we need also power supply for our trains. We need communication, we need signaling, and so on and so forth. And last but not least, maybe I should also mention this, we as a society using those networks, so we also have to account for us and for our interactions, so this human physical interactions. One thing, what our infrastructure is physically embedded in our space, so it's not somewhere in an empty vacuum. We use them on a daily basis, so in our cities and so on and so forth. However, since this is also embedded in space, we are those infrastructure systems are quite prone to natural hazards since they are very large scale, and due to this complex structure, one failure in a very small part can cascade dramatically and have huge impacts on our society. Another thing about the world we're living in, I guess it's hard to neglect this fact that there are changes in our environment due to densification of our cities, due to different land use, and also due to climate change. We will see different scenarios in the upcoming years. And I found this chart recently from the Metro office in the UK, which shows the average rainfall amount in February 2020 compared with the rainfall amount over the last, so for February over the last, between 1981 and 2010. And what they show here nicely, or at least what they show in this graph, is that there is obviously more rainfall, which might lead to more natural hazard events, maybe more flood events. Yeah. And this is another example I found. It's a city in Germany, quite close to Zurich, where I did my PhD. So it's roughly 100 kilometers away. It's the city of Degendorf. And in 2013, there was a big flood in Germany, or along the Danube. And this was more or less the result out of this flood. So you see more or less the whole city was flooded. The highway, which is a major highway connecting parts of South Germany with Austria, was completely flooded. So no one actually could enter the city and leave the city. And exactly this is what I'm interested in, to study this phenomena and see also what caused this flood event, and also, of course, the engineering idea, can we prevent this for the next event? So that how can we change the system in order to make it more resilient against those natural hazard events? And in the first part of my presentation, I like to tackle this on a with a more engineering point of view. Well, I'd like to talk about computational modeling, so breaking this apart and model physical behavior in order to reproduce those events, and then see when we change something in our model, how does this might affect the system, and are there smart options in order to prevent such failures in the next few years. Sounds easy, but everyone who already started with modeling and simulation knows that it's, I guess it sounds easy to do some simulation, but actually it's hard work. And especially when we're dealing with natural hazard. Why? Because we cannot only focus on the hazard itself. So the hazard itself is only one part of those. So we have to think also about the source event. So for instance, when we're talking about this flood event I mentioned before, was it caused by additional rainfall, a dam breach? When there was additional rainfall, how was the runoff? Can we model those? Then the next step is, of course, the hazard alone doesn't impact us very much, but the combination between the hazard and our infrastructure objects. So now this bridge more or less cannot be used for a certain amount of time. And this, again, has effects on the network structure. So this bridge might lead to a remote valley somewhere in the Swiss Alps, and people have now to take huge detours, or in the worst case, even cannot enter this valley anymore. And so in order to make this, avoid those, we have to also consider how these objects react with the hazard, but also how these objects influence our networks. And then last but not least, we as a society, we are using those networks. So at the end of the day, we have to rebuild those bridges, but also we lose money and time and maybe human lives because we cannot use the networks as they are supposed to be. And so for all of those 5 steps, simply speaking, when we like to computational or to model those events, we have to take those into account. Probably no surprise for you, but we can do this. There are a lot of people working in each field, developing very efficient and very precise models. So we have, for each of the events, we can break them down into several models. Here it's only systematic or schematically described. So every model or every event more or less can be broken down into a model. And then since we're dealing here with spatial temporal changes, so we have spatial boundaries for all of the models. We have a temporal evolution of the model. And then of course, we're dealing here with events, which happens very rarely. So we have a lot of uncertainty if they happen and when such an event happens, how does this affect other events in this chain? So again, we can have different intensities of rainfall, which ends up in different flood events. This can have different impacts in our infrastructure and so on and so forth. Then we have this cascading event. Yeah. So to go a little bit from the more abstract to more concrete point of view, I'd like to focus the rest of my presentation here on this case study and all the models and ideas I would present on this compact case study. So this case study was conducted together with the Tiefbauamt, the engineering corpus of the canton of Grissom, which is the Easters canton in Switzerland. So this was the area I will talk about. This is the main capital of Grissom, that's Chur, which has roughly 30,000 inhabitants. Then there's a very important highway going through Chur, which connects more or less Austria, the northern part of Switzerland, and Germany with the southern part of Switzerland and Italy. Also, what you see here are historic events, recorded events. So we know that this area is actually quite prone to flooding and landslides. So yeah, that will also be a part later in my talk. So it's not only modeling the stuff, but also taking previous events into account. What you also see here with these gray dots are more or less bridges, which might be of interest for us. So this is more or less the case study I like now to show you the ideas and the tools we developed. So coming back, the first thing what we need, also with this picture in mind before, with this very simple 5 pillars, is simulation models, more or less. And so what we created is a simulation engine where you actually can couple different models from different persons together. So for instance here, this is what we're going to explore in this Chur region. So we have here a model, for instance, a rainfall model, might be based on satellite data. And this rainfall model is needed in order to create a runoff model. And this runoff model later on gives data to the flood model. And if the flood occurs, it affects, in this case, for this scenario, either bridges and road sections. And those objects can then either have different functional capacity losses or speed reductions, which have effect on the network. And either we have to restore the network, but also another thing which what we're interested in is, for instance, the diversion of the traffic flow. And then last but not least, as I said before, our society has to bury the costs in form of direct costs, which is needed for restoring the objects, or indirect costs, which we experience due to traffic delays, for instance. So what we have done in this is more or less, we created this in simulation engine where you can plug in your computational model, and then the simulation engine more or less plugs it together and takes information needed from the previous models in order to run those simulations. Yeah, I guess it's the easiest ways to show such a simulation run. So here, what you see again is the Chur area. I will play afterwards a short video. We have here different time steps. So the temporal resolution is in hours. What you will see is that from the top, there will be a rain cloud coming over this area. This rain cloud leads to additional discharge in all of those rivers, and then later causes a flood event in certain areas of this city, which causes damage to either the road or the bridge infrastructure, and also leads finally to a diversion of the traffic flow so that people cannot move anymore. Also, what I forgot to mention before, so this is not only a single hazard, but this is a multi-hazard scenario. So we consider here flood events, but also rainfall triggered mud flows. Yeah, I guess the best is now to run the simulation or the record more or less. See if it's, yeah, plays something. I hope you can see this too. So now, as I said before, you see this blue rain cloud coming over this area. The water increases in the river, leads to damages of the infrastructure, which causes people to use other routes through this network. This is now a simulation for a 500-year flood event. And of course, when we do simulations, we not only can run this for one example, but we can run this multiple times. And this is now the same simulation I showed you before for the same flood event, so a 500-year flood event. However, we run this multiple times, and since we're using probabilistic models, we're getting these types of flood or maps. So what you see here is more like a agglomeration of different floodplains, and 5% of the floodplains do not exceed this area, and 95% of the floodplain more or less cover this area. The same is true for the mud flows. So these are possible mud flows which can occur in this area. So this is more like, yeah, probabilistic modeling of this very rare event. Of course, this can only be this cannot only be done for the physical damage, but also for the costs. So what we see here is plotted the main impact of this flood event, again, this 500-year flood event of our society. We see here a diversion of traffic flow. Of course, the traffic flow in the city is increasing, so also the people have to diverge to this route and cannot use this route anymore. And here with this hotspot, we see more or less where we expect the majority of the restoration costs. Of course, this is only one step. So now we more or less destroyed the system. However, in order to be resilient and to have resilient infrastructure, we also have to think about now when we have this broken system, how can we bring it back to something which works again? So how long does it take? Where should we put our effort? Is there or are there optimal strategies how we can handle such events if they occur? So if an event occurs, what are the best strategies? And this, we call it restoration models. So where can we deploy which restoration workflow in order to bring the system back to a certain level of service in a certain amount of time. Here, a very, very simple restoration model. Of course, that can be much more complicated, but yeah, it's more like to show the idea that we're not only needing the hazards and how they impact our infrastructure, but also how we react to those hazards. So what we see here, again, is we have direct costs, so money we spend to rebuild the system. However, on the other side, we have impacts on our on the users. In this case, it's represented by traffic costs and also loss of connectivity. So that the worst case is people can actually not travel at all. This would be the worst case, which also means that ambulances maybe cannot reach people who need them, or people cannot reach hospitals and so on and so forth. So this is of all costs, we should avoid this. However, also when there's a huge traffic jam and you need hours to go to work or reach critical facilities, this should also be reduced. However, this is an optimization problem in this case, since we can spend a lot of money in order to do it fast. The question is, do we need to spend all this money, and also which object should be done in which sequence? So again, a quick video. It's not very meaningful, but it's yeah, showing. So we have now 3 workflows for the same scenario I showed you before, and here is the first. So this time steps is 9 day, and the first day people the workflow start somewhere and then move around in the most optimal way. This is more like what you get out of those algorithms. What you see here, again, are 3 workflows you saw before in this video. So workflow A, B, and C. You see here the time horizon for this scenario. So we need in total 40 days to restore the system to 100% more or less. And here you're getting more or less a restoration schedule. So what's the most optimal way to do this? So in terms of which object should be done first, and it's a little bit hard to see, but which strategy should be used. And we compared this with the classical strategy, which is more like ranking different objects based on the daily traffic volume. That's what's currently implemented in Core. So they have historic measurements of what roads are most used. And then they rebuild it based on this ranking. However, we can show that actually with a little bit more thinking, even with very simple models, we can produce better results. Whoops. Yeah. Okay, and of course, this is again a probabilistic procedure. So when we run multiple simulations, we actually end up with such curves where we have this uncertainty again between the best, the worst case scenario. And what we also can do is run for multiple scenarios. So what I showed you before was only for 500-year flood event. However, we can do this for 10-year, for 100-year, for 1,000-year flood event. And then we're getting these curves and see the trajectory over time. However, the big disadvantage about doing this, and probably everyone who's doing simulation knows this, that this is a very time-consuming process. So especially when we're dealing with 2 to 3-dimensional flood models, when we're dealing with traffic flows, when we're dealing with agent-based models, where we actually like to model each person as an individual, then it's very computational intense. And there are multiple ways how to avoid those. And one of those is not using or running some simulations with the engineering models, but then coming up with surrogate models in order to speed up those processes. And I guess people who saw a talk from Bruno Soutre are familiar. So I borrowed this slide from him, more or less showing where the approach I presented you before fits in. So this is more like the computational modeling part, where we can plug in different models, run simulations. However, then there is the need of smart ways to model those computational intense simulations. And the second point, what's also shown here, is we are talking about uncertain events. We don't know if they happen or not. So the question is, how can we deal with those uncertainties? How can we actually figure out what is most sensitive? And this is research I like to do in the future, especially since now this simulation engine exists. We can run engineering simulations. The question is, for instance, do I need this very expensive rainfall model, or is actually most of the uncertainty related to my flood model, and so on and so forth. So there are questions. These are questions I like to answer in the future, and maybe there's also some interest from your side. Of course, so to summarize this, we can simulate the events. Now we have efficient tools to restore the events. However, as an engineer and also as a society, we don't like to see that our infrastructure breaks down and then say, oh, now we have a smart way to restore this. Actually, what we actually want to see is avoid this in the first place. And I use this picture here because it's quite nice. It's the same flood event as I showed you before in Degendorf in Germany, but this is 120 kilometers downstream in Austria, in Grein. The same event, the same day, but they invested into this flood protection walls, and it seems, yeah, they at least could avoid the severe impact of the flood event. And actually, this can also be done and is already implemented in our simulation engine. So what we played around is exactly those features. So people, engineers, urban planners can take the simulation model and change the parameters, and then it will recalculate, and you're getting another feedback. So this is, again, the city of Chur. This is the northern part. It's a small village called Haltenstein. And when we run the flood model, we will see that actually the village is completely flooded. The buildings have severe damage, and also the road network. And we gave the opportunity to city planners, urban planners, and also the local Tiefbauamt to play a little bit around and draw more or less a flood wall like you saw before in the picture. So when you draw this flood wall here, you see we actually can avoid most of the risk related to this village. However, on the other side, what we see also that these consequences of having this flood wall is now that this major highway, which is a major connection, as I mentioned before, would be we expect here more severe damage than in this scenario. So then we have to more or less wait what now we like to do, or maybe there's a third way, another smart way. And as I said, this was tested out. So we created this user interface where people actually can test out different scenarios and see when they do the changes. So also you can also decide in a timely manner. So you say, oh, you wait 10 hours and then you do something, or you do it immediately, and so on and so forth. And you can run different simulations. Which more or less concludes now what was already done. Now I'd like to give you a quick outlook on what I'm actually currently working on and where this computational simulation can go in the future. And I put here a very recent graph. I think many of you already saw this, and I guess it's a very, I guess this page has over the last couple of months a quite high frequency of users and people who look at it. This is the current COVID data. And this is online available for everyone in the web. However, this is only a dashboard. So you only can receive information. So you cannot do anything with it. You can go there, you can look certain things up. Yeah. And another interesting thing why I put this up, even it's not really related with my research, in this case is, well, not really, a little bit related, let's say this. So when we zoom in, this is Switzerland, and what you see here is Zurich. Yeah, why I put this in is with the framework I showed you before, we used this actually 2019 and simulated epidemic spreading in Zurich, not due to COVID, but to normal influenza. And let's go further and let's see if this is working. So now you should see a movie where this is an agent-based model. So every user in this network is a person or a vehicle, and then they come to Zurich, start working, and in red you see infected people. So we located them randomly, and then they move around, have the daily interactions, go to work, meet other people, and then there's a certain probability that they can infect other peoples, and you see the numbers per one day, and then you can run this over multiple days, and you see how these numbers increase as we now see live, more or less. However, yeah, as I said, this is what we have done before. And then also we implemented that people actually heal and recover. And so we can see what we've done here was simulating more like this spreading. But what we wanted to show here is not the spreading itself. It's more like that even as a civil engineer, we can contribute to this discussion with our knowledge. So what we figured out is actually that epidemiologists, they don't have those traffic flow models. So what they're using are different types, but what we are doing is actually very precise. We're using this to model traffic flow to make decisions about our road infrastructure. And why not providing this information to other people so that they can access it? And this is more or less the vision I have, and what two of my colleagues and I am working on is bringing this engineering knowledge into the cloud, allowing those, oops, too much here, allowing users more or less log into a web page and using the same tools as we had before. So they can more or less the same scenario as you saw, as I showed you before with Core, they can plug in their own scenario, run simulations in the cloud. So this will be distributed on high performance computing and then getting the results back. And here you see some mock-ups and work in progress. What we're aiming for with this project, again, it's more like making it public for a bigger audience, utilizing high performance computing, making it very easy to create their own models and run simulations on the cloud models. So that's one research project I'm focusing on currently. Okay, let's take a big leap before we come to the second part of this presentation, leaving the engineering world and going more towards a mathematical approach. So what I showed you before was work on infrastructure networks, and networks in the easiest way can be expressed as vertices and edges, which is more like a more mathematical way to address those issues. And also there are very interesting questions which arise. First of all, network science gained again popularity in the last couple of years. However, most people who do network science are actually working on social networks, internet, and only a very small amount of people working on infrastructure networks. It seems not so sexy, I guess. I'm not sure. However, so when we're talking about infrastructure networks, they're actually quite interesting because, first of all, our infrastructures are spatially embedded. So what we need is actually space where we can put our networks. So they occupy space, which means there are certain rules in order how they can be connected and what actually might be connected. The second thing is when we're talking about infrastructure, they're actually complex and interdependent. So I can have, for instance, a highway network and then a lower road network, and they are connected. And when something happens on the highway, we might see traffic jams on the lower detour routes. And then, of course, the next part is that we not only have one system, however, we have a systems of systems. So that the road network is needed in order to reach power facilities, a power grid is needed to run our pumps or to run the railway. So we have this interdependent systems of systems. And now network science provides a an elegant, mathematical elegant way to describe such complex systems. However, first of all, we have to get a little bit more familiar with this. So as I said, networks, spatially embedded networks are not so much under investigation. So what we have done is thinking about, so when we have a spatial embedded network, how would be a null model look like? So more like what might be a mathematical description to recreate a real world network in the most simplest terms so that we can use it later for our simulations or to test our hypothesis. So when we change something on the network structure. And what we came up with something we call multi-layer spatially embedded random networks. So what does this say is we have multiple levels of hierarchies. As I showed you before, we can have highways, we can have power grids, spatially embedded, so they are embedded in real world space, and random because we're not now using a real world network, but we're creating an artificial network which mimics or tries to mimic more or less the reality. Some quick overview. So I'm not going into the detail about the math, and there are papers out there where it's explained in more detail, but more or less, as I said before, the main ingredients of network is we need a set of vertices and a set of edges, and they have to be connected somehow. However, when we're talking about spatial embedded networks, what does this mean? Our nodes, for instance, highway intersections or power distributions have to be located in space, and they interact with each other. So it makes no sense to have two highway crossings quite close to each other. Normally they are spread out quite widely and so on and so forth. So they interact with each other, but also with their embedding space. The second one is when we're talking about edges, most people actually model edges only as a connection between two vertices. However, that's not true. When we're talking about a road network, or again, power grid, or any other spatially embedded infrastructure network, actually the space matters. So we're not normally don't draw a straight line between two cities. Normally we try to minimize the cost of building those roads or power lines. And we can account this also with various connection models. And yeah, that's what we investigated in our multi-layer spatially embedded random network model. And I'd like to show you some results. So what you see before, again, this is the core example. But now with a completely random network. And as a human being, you actually can quite see that this is not the real network. However, when you analyze this network in a mathematical sense, so you take some network properties and compare it with the real world observations, then for a computer, this network look very, very similar to the real world network. So they cannot make a distinction between these. What we also can show is now we can use those artificial networks in order to test our hypothesis and test how robust they are against attacks or damages. And what we've done here is called percolation, which is a very simple tool in network science. It means we remove randomly edges and see how the largest connected component of the network behaves, or we remove edges or nodes in a tag with some clever algorithms in mind, for instance, the most central node or something like that, and then we're getting those target attacks. What we see here, so in the bold line is the real world network, and our random network is more or less around here. You see that we get very similar behaviors either in the case when we targetly remove nodes or when we randomly remove nodes. So this means we can use those networks again to test our hypothesis. Yes, and then one nice thing about mathematical models in general is they can be scaled up quite nicely. And so we can leave the small city of Chur and extend it to a national grid, for instance, whole Switzerland, and it's more or less similar, not much more computational time to analyze or create those random networks for whole Switzerland. So what you see here in the middle is the real world network, and on the right side, you see the artificially generated network, in black the power lines, and in white the roads. You see there are some differences, however, there's also some similarities you can find out here. The same thing here. Here we decided to use highways and secondary roads, again compared with the real world network. So now we understand at least a little bit more how we can model the physical infrastructure. However, as engineers and this is, people who are dealing with those networks, we're not only interested in the physical infrastructure, but we're also interested, or mainly interested, in the functionality, so in the dynamics, in the network dynamics, because we're using those networks in order to go from A to B, to transport information, to transport goods, and so on and so forth. So we're not only interested in the structural part, but also the dynamics part of the network. And one simple and often used idea in network science is a diffusion process. So this is also one of the main processes which is used for epidemic spreading. Again, so we have a random walker walking through the network, and that every cross-section he decides randomly where he likes to go. It's a very simple, nice mathematical model. However, it fails completely when we're talking about infrastructure networks. Why? Because with this random walker, we completely neglect that the infrastructure network is here for purpose. The purpose is to transport, as I said before, stuff from A to B. So we have some kind of origin destination. And what you see here with these relative differences, so we compare here this random walker, this diffusion process, with a classical engineering simulation of the traffic flow, and we see we overestimate traffic flow quite a lot in especially remote areas, because the random walker walks there, they don't have any preferences, they don't have any goal to go there. The idea was now, can we find actually simple model to account for this fact that we have this origin destination information. And what we came up with is a networks in networks model, which more or less decompose the network and then recompose it into a different way. So we don't need more information than the original network. So what you see here is this example network. So we have this small original network. However, now we structured in such a way that we're not describing the network based on this topology, but we're splitting it up and say, okay, what are possible paths from this node to this node, for instance. So there are multiple different paths. So we encode this information also in this network. And then we combine those paths which going from the same node, from the same origin node to the same target node, which is in this origin destination path, more or less. And the last is this origin destination network, where we again combine all the paths to each other. So that the main point or the main takeaway of this slide is that we can reconstruct this network in a different way, only using the same basic information about the vertices and how they're connected in order to encode more information into our network. What we can do here now is then run again this very simple percolation models, however, on different subsets of those networks. For instance, we can run it now on this origin destination path network, which is we remove here an edge, and then suddenly this path is not any option anymore. So people have now to move away from this path to another path in order to go from A to B. So this is then, again, the same diffusion process, but now we have some physical meaning behind it. And when we do this, for instance, for the core network, what you see here is, again, the same picture, the same relative difference comparison with the classical engineering simulation model before. However, we see now that when we capture this origin destination information, we're getting much better prediction about those remote areas. So we don't have these huge outliers. Another nice thing about using networks and network science is it's very fast, since we only have some matrix algebra. And here, I only put this here to showcase it. So there's nothing optimized either in the traffic assignment model nor in this network models. However, there is a factor then 100 that we increase by using those network methods. Of course, they're not as precise as engineering models. However, for a quick estimate about what would change when you remove an edge, this might be a quite feasible solution to get a first impression. Which leads me now to the last part of this talk. And this is a higher order network model. So that's what I'm currently working on. And this is one step going further. So before I showed you, we have information about the topology. We have information about network dynamics, but not really, because it's only based on the topology. However, we are living in a world where we have tools like smartphones, which track all our motion. We have GPS sensors, we have satellite data. So we have a lot of information actually available where we can track the movement of our people, the mobility, cell phone data. The question is, can we utilize those information in order to make better predictions where people move, and also what might change when you change the underlying topology. So that's the last part of this presentation. I'd like to talk about this higher order network models. And so the idea here is that we're not creating the network based on the underlying topology, but we're using more or less information on top of it. So for instance, time-stamped data. So we have here a person who's going from A to B and then from B to C in this sequence. And there are multiple interactions between those four connections. And when we sum this up, we're ending up again with this static network, what we saw before. However, each of those interactions is now in a timely manner, more or less. So first it happens this, and then people moving around. And when we sum up all of their behaviors, we're ending up with this. And we see in this static network representation that 8 people move from A to B. However, we don't have the information about when this happens or what they did afterwards. Which leads to the problem that we can have exactly the same final network, the static network as before, with the same number. So 8 people move from A to B. However, we change that there's actually no the possibility that you go from A to B. So it might be the case that you taking the train from A to B, but then you miss your connection train and you have to wait instead of can directly take this. However, when you have the static perspective of the network, you actually lose those information. Talking about trains, so this is this analysis, what Ingo, my currently corroborated Uni Zurich now was doing before. So what we have here is the London Tube network, so the underground network in London. And here this is a diffusion process where we take into account the previous steps of the people. So what you see here is diffusion and people moving around in this network, and then they will diffuse throughout this network. When we don't have this information about the sequence, how they move, then we will get this behavior, which is completely random, and we again lose information about how people move throughout this network. So maybe I can play both at the same time. Let's see if this is working. So when you compare now both, we see in the first network that there's more or less a single instance moving around, and then it's spreading out, while on the right-hand side, it's more evenly spread out. So the question is now, how can we address those dynamics? How can we take into account, again, more information about our past with those network models? So to recap this, this is the static representation, and this is good when we don't know anything. So when we don't have any information about the network, we only have the topology, then this is a perfect model. However, in many cases, we have more, and we not only can model the static network, we can also encode the information about where we were before. So we have some kind of Markovian process. We know where we came before, and then we're going to the next point. So what we're showing here is now we combine node A and node B in order to have a node AB, which describes, this node describes more or less the edge AB. So we know when on this node, we come from A and go to B. This is called a higher order network because now we have the information of the previous step, and we can increase the order. So this is order of 2. When we have order of 3, it means we have also the information before. Maybe you have CA, AB together in one node. This allows us now to distinguish these two cases as we had before, where we can actually go from A to B to C, or we only can go from A to B and then only go from B to C. So this is the first network, the blue one, and this is the green one, and we see that the link in the middle is missing. And so with this idea, we can create higher order network models in order to better describe the data we actually observe in the real world. And of course, there are a couple of questions related with this. The first one is, what is the correct order? To which magnitude should I go? And when actually is a network model sufficient enough, so that the basic network model, when do we have to go to higher order network models and so on? And this more or less is a machine learning problem. And this is also what we're currently doing in this project I'm working on at University Zurich. However, this would be a much longer talk, and I'll leave this more or less open for maybe a future talk. Maybe before I conclude, there is a lot of literature, research is done on those higher order networks, and it's becoming more and more prominent because they can be used to find centralities, to rank nodes in a more realistic way. They can be used, for instance, to find anomalies, what shouldn't happen in a network. Also, what we can use, and there will be a recent soon a paper out, is predicting paths. So we know where people are coming from, then we can predict where they actually want to go, or we can cluster paths and say, okay, this a certain user group which are using this system, or a certain user group using this system, and we can classify those paths. And what I'm working on, and you're happy to join and test it out, is PathPy, which is a Python library which actually does this machine learning part for you. So you give them data, and then PathPy will more or less train the model, and then you can make predictions based on your path data. Yeah, that's more or less the end of my presentation. More information about my research and the projects and publications can be found online on my homepage, hackl.science. And also, if you're interested, there will be a talk at ICOSA next year about a symposium with scientific software tools, where I present some of the tools are presented today here, and also a lot of other interesting people present their tools. So thank you very much, and if you have any questions, please feel free to ask them.
Yes, thank you, Jürgen. Yeah, thank you for the interesting talk. If people have any questions, there should be an option to raise your hand in the chat, I think. So if you're able to do that. Yeah, Marco, you have a question, I believe.
Hi, yes, thanks, Simon. Thank you very much, Jürgen. It was a very interesting presentation. I think I have a couple of questions, but I think I ask one, then if others have other questions, I let. On slide 13, I noticed that in your graph on return period, something that is a little bit counterintuitive. I mean, I would expect, I mean, you're presenting some costs scenarios. Well, is a cost graph as a function of return period.
Yeah.
I interpret those bounds, I mean, those shaded area, like the yellow and the gray one, as some sort of uncertainty bands on the costs. So I wonder why, as the return period increases, these uncertainty bands get narrower. Is there an explanation for that?
So I think that there are two problems with this plot here. We figured this out late after we run hundreds of simulations. First of all is that this is a multi-hazard approach. So where we have mud flow events and flood events. And the problem was here that the mud flow event shoots more or less the flood event. That's the first thing. So that's why we especially why we see already at this very low return periods, this very high costs. That was one observation we had. And the second one, why this is getting narrower, is because we force a lot of flood, more or less, and rainfall in this area, and we will always end up with a very high damage scenario. However, we destroy more or less everything in this 10,000 year return period, more or less. And so we always end up with, I think that's why we end getting this very narrow uncertainty bounds, because the sheer amount of rainfall which going down there is causing.
So is it because there are like some sort of overlapping events, and you're showing only the results of one?
Exactly.
While, I mean, bringing them to all back together would result in an increasing uncertainty bands. Is that what you expect to see if you were to include all of the factors that are not presented in the plot? I mean, I'm just wondering if this is like intrinsic in the methodology that you're using, or is it because like it's showing only one aspect of?
So this has nothing to do with methodology. It has mainly to do with the case study we worked on, more or less, and how we choose the example. The methodology is very simple. It's more like you simulate everything and then it pushes it further to the next model and then so on and so forth. However, I think, and also that's an open task, a to-do task, and I pointed it out in this slide here, is what we've done here in the first presentations was really brute force simulation. So we didn't consider any sensitivity analysis of the models, which influences what. The next step, in order to find out why this strange behavior happens, is to see which model actually most counts for those uncertainties.
Okay, thanks for your clarification. I think it would be interesting anyway to see how, contrarily to brute force approaches, how would perhaps more, uncertainty, hardcore intrusive approaches would compare with that. But that's just a thought. I mean, so something to think about. I guess I leave space to others. Then maybe if there is more time, I'll ask another one. Thanks.
Yeah, hi. I don't know if I'm meant to speak.
No, go on.
I don't mind. I'll go after you. Okay.
All right. Yeah. So this is just pertaining the surrogate modeling bit. You use the neural network.
No, there is no surrogate model. So that's more or less steps for the next for research, more or less open research and how to implement it. So what we've more or less done here was more like presenting simulation engines. You can put in there any model what you want, more or less. It's like the idea is the simulation engine more or less coordinates the simulation approaches. You give them a rainfall model. It can be a surrogate model or it can be a highly computational intense model. And then what our software is doing is now taking this information, processing this information, storing this information, puts it further to another model which needs those information.
Okay. Yeah.
So there's no surrogate models involved yet. That's also why it's now very computational heavy models.
Okay. Well, can you parallelize this whole process?
Yes, yeah. That's also what the tool is doing. So the tool is if the given model is itself parallelized and it utilizes this functionality. If not, then it does it in terms of running one model on one thread, more or less. But it does it automatically.
Okay.
And also it schedules more or less different. Let's go back to this one. Different models. So more or less, so every point here is a computation model, or it can be a surrogate model. And what our simulation engine is doing is looking, the runoff model needs some kind of rainfall input data. Is the rainfall model available? If yes, please run the simulation. And then it will ask the rainfall model. This produces some information, push it then to the runoff model, which is done automatically. Since we have this temporal component inside, which makes it even a little bit more tricky because the rainfall model is progressing in time and space, and also runoff model. And so this has to be coupled in a clever way in order to run those simulations. And so that the main focus here was not so much really on each model itself. So we used very off-the-shelf standard models, very simple models. And this can be later then replaced by more substantial models or surrogate models and so on and so forth. Our main point here was really to make these connections and to have this simulation engine which pulls and pushes information to the underlying models what you need.
Okay.
So that was the idea.
Thanks.
Excellent. Adolphus, do you have a question at all?
Yeah, I do. Thank you so much, Simon. Also, good afternoon, Professor Jürgen. So thank you so much for your insightful discussion this afternoon. So my question is mainly pertaining to the first part of the presentation, whereby we discussed about the framework which you use in this computation and simulation of the system of the city. So we have a source event, and then you look at the hazard, the object, and then analyze the effect of the network and how society actually responds to the source event. Now, I was thinking of this entire, looking at this entire framework that we discussed, and I was wondering if, because what we have been looking at so far is mainly at at the disaster response of the society to the to whatever that happens in the city. But could this be used in like you know in the sense that if let's say we have a like in city planning, like let's say if you have like an area whereby you're starting to build up cities and then all that, and you do not have any prior data or anything, what you have are only like the weather conditions in the area, because when you build an area, the weather condition in the area doesn't change with history. So I was wondering if this framework that we discussed could actually be applied in city planning, and eventually, you know, in disaster mitigation rather than prevention.
Yes, yeah, it can be. And also I showed you one example which was run with the same engine, which was more like this one here, where you use the same engine, but there we had another node where you could actually make choices, more or less. You had the choice to draw a flood wall, more or less. And so people could interact with the models, plan something out, and see how the things will change. So in this case, when you draw the flood wall, you have increased elevation, so that the DTM, the underlying DTM, was changed, which changes the runoff model because the runoff model is heavily dependent on the DTM, which changes the flood model because then you have the higher DTM and then the flood cannot go over this. However, it can be overtopping when you have another event. So there you can actually interact with those models in this sense. I guess you can do the same then for city and urban planning. So you can draw a new road, more or less, and then people can use those roads. Yeah, guess that should be possible. We never tried it out, but I guess the option should be there. So you modify the underlying data, and then the engine more or less recalculates the simulation again.
Thank you so much, Professor.
Okay, just like to add on to that, I was wondering, the data set you're based on, I'm guessing, is topographic, and I was wondering if there's any additional, I suppose, prior data you could add to it. For example, the effects of different land use on the flow. Is that being considered in the model at all? Or is that
so what we also used here is also for the flood model, again, it depends on the level of detail you actually want to consider. What we have done here is we used a very simple one-dimensional flood model, one plus two-dimensional flood model, let's say this, where we used the land use as an approximation about the roughness coefficient of the surroundings, more or less. So this is included there. However, this depends then on the model itself. So you can also plug in a three-dimensional flood model, which of course is huge in computational time, and you need a lot of additional information about how to set this up. But this is more like encapsulated in this small thing. So what you have to define is more or less the API and say, okay, this model can provide us with flow, shear, velocity, and so on and so forth. And this will be provided by this model. And this model needs this and this and this input. And then the engine screens will say, I need this input. And it can either be provided directly as a maybe shapefile, or it can be produced by another model using a certain type of data framework. And then this even 3D model can further push out then maybe the flow velocity, and this can be used by another model. So you have to specify the API, how to interact with your specific model. Okay. And of course, data can be used not only by one model. So when you have the land use data, you can use this also for other models. I don't have now information about the land use data, but for instance, what we've done and considered is that the rainfall data influences maybe the traffic model. So there's a more rainfall, people driving slower. So the influence is more or less the network in terms of the average speed is going down because there's more rainfall. So you use the rainfall data not only for the runoff model, but also for the traffic flow model. However, then it's up to you how to define this traffic flow model. So normal traffic flow model don't consider this. So you have to write a small piece of code which says, okay, if the rainfall is this and this amount, in this section, the velocity will be reduced or something like
that. So I suppose, can you also, if you are using, for example, a vector file to suggest roughness, I was wondering, I think conceptually, is there a way to kind of apply or stratigraphy the costs of these hazards as well? For example, if I want to look at the differences between costs on high-income neighborhoods versus low-income neighborhoods, or recovery times between those two, just because I think the costs are usually disproportionately applied. Is that a possibility at all?
So not yet, but the idea would be that as user you can interact with data. You have more or less a common data storage where you can store different geolocated or temporal data, and then you can access those and make queries on those and ask, okay, this is now a low neighborhood area, should we spend money there? But this is ongoing research and also a project I like to develop further. And it's more really to give the user the ability to use those information and add their knowledge to it. Because what we figured out, which is quite tough actually, is to be an expert in all those fields, and that's not possible. And I never claim that I'm an expert in flooding or landslides or mud flows. And there are people that do brilliant work there. They have the best models there. However, it's very hard for us as researchers to get their code and then re-implementing it in our code and then so on and so forth. And the idea here, and also for this future research, would be to have these modulars where every researcher can contribute in his field of domain and provide it on an open platform, and people can use and say, okay, yeah, I know he's doing a good modeling in traffic management. I use his model on this platform, and I'm building up a social model and any other model. So that would be the long-term vision about this type. So it's not really about the models itself. It's more like how to bring this information together. That's one of my big research interests.
Okay, sure. Is there any further questions going on? Mark, you might have a couple more.
I don't seem to be able to raise my hand, but I have a question. Okay. Actually, I have 3 questions, but like Marco, I'll defer. The first is on like slides 10 and 11 and 12, you were talking about the restoration costs and finding, it seemed like you were asking is it the case that you were saying, asking of the simulation, which restoration scenario is going to be the most efficient? Is
exactly,
that?
Yes, yeah.
And on slide 12, you actually concluded by saying, with a little more thinking, we could be smart about this choice. Is that what you were also saying?
Yes, yeah.
So my question is, why don't we have to think at all? Why can't we make the computer do the thinking? And
that's what the computer is doing.
It is doing that, okay.
Yeah,
so
the computer is optimizing more or less the best strategy here.
Okay.
We give them the set and say, these are the damaged bridges, that is the estimated damage, and those are the options you can have, these are the resources you have. Please find the best way to do this. That's what is implemented here.
Right, okay. And it's using genetic algorithms or something?
In this case, yes, yeah.
Okay.
One further idea, and what we are now trying to do, is going towards machine learning, so reinforcement learning, where you play a game more or less and figure out by playing the game what's the best strategy. And the idea would be then not only doing it, also training it on this and then see what happens when you apply this to another set of bridges, how the computer plays in this scenario.
You would like your algorithms and your approach to be smart enough to maybe come up with the option that the right way to repair the bridges is to move the people onto the other side of the river. Maybe would that be a possibility? That sort of out-of-the-box thinking that everybody's so fond of. We would like our computers to be able to say that to us rather than pick from a limited list of options. Is that a possibility, or how would you imagine taking that sort of flexibility into account?
Sorry, can you repeat this? So the idea was to...
Well, instead of, for instance, maybe the optimum restoration strategy is not to restore, but rather to move people from the one side that flooded to the other side of the bridge so they don't have to you wouldn't repair those bridges. You know, like we often say about people who build houses in flood-prone areas, the right solution is to not rebuild or put them on stilts, but to not build there. So my question is, can you imagine this sort of approach to be general enough, to be flexible enough, to do some outside of the box thinking that would enable it to come up with such solutions? Like, you know, humans do all the time, but it's harder for computers.
Yes, that's an interesting question. But however, I guess you have to then to see again that it's big picture then. So
Yes.
then the simulation, and then I guess you can play around and figure out what's the optimal strategy, and maybe say you should resettle everything because the computer figures out that this might be the most suited.
Right. And then
I guess there might be an interesting idea to play it out and see.
I've talked to people about this, and they say, yeah, we're doing that, and then, but they're not ready for the next question, which was, you know, when you take into account everything, then you also can get bizarre solutions. You know, for instance, if you want to minimize the number of deaths, of human deaths, the most efficient strategy would be to kill everybody right now, because that way the future deaths will be precluded, right? So there are lots of rather unpleasant outcomes that are possible too.
I guess the same can happen here. They say then, oh, no one should live in Chur anymore. They should all move to Zurich or something like that. And, then everyone would be safe in Chur at least, because the risk in Zurich getting flooded is minimal. So I guess that's some big question which going beyond the pure modeling. And of course, the models is only garbage in, garbage out. So I guess that's where we as scientists are asked to ask the right questions and be critical with the results.
So it seems like your model, or this approach or tool, you've been calling it a tool, this tool can do kind of like, what can't it do?
So actually, it's quite simple. It's more like
models mostly.
It's more like scheduling and calling the right models to the right time. That's all what they're doing. It's more like a management tool. So you give them a model and say, this is the input it needs, that's the output they can produce. Then you plug it in, and the tool, more or less, or the simulation engine, more or less, when you connect those different boxes that knows, okay, this is connected to this, so we have to run this first, and then it looks, is this can this be run on multiple cores or not? And then it schedules it. So it's more like a scheduler of engineering models.
So is the input, is the communication between the software packages, is it?
Yeah, you have to define an API. So you have to write your
API. Okay. Yeah. So you define an API, and but more than that, the data itself, so not just like what to do, but what numbers to use. Those are file mediated, like spatial files.
So what you can do is either you can have it in a global storage, where you only can store dedicated files like shape files and what we support more or less. And then it's stored there, and then the engine can take it out there. However, there are special needs for certain softwares where they have, for instance, a config file, which is an XML file for an agent-based transportation model, which is only unique to this specific agent-based model, and no one else uses it.
Right.
So then you can attach it to this model, and then this is more or less in its own bubble, independent of all the others. But when you say, oh, this agent-based model actually should access a network, which is not only used by this model, but maybe used by the national hazard model as well, then you store it into the other database. And then you have to write the API to get this network for this model. But what you have to do is more like writing APIs for your code.
That sounds like a lot of work, though. I mean,
yeah, and it's guess coming up with a sophisticated engineering model for this purposes is much more complicated than writing a simple API saying you need this input data and then you can run this model more or less.
So, but it leaves, what I'm saying is that it leaves the responsibility to do that to the modeler effectively. There's no generic way to say, I mean, we've been talking about linking models together for 30 years in computer, right? And people generally say, oh, it's going to happen via a spatial model. So one model affects one model takes the rainfall and figures out where the water is deposited, and then another model looks at the elevations and the slopes and figures out where the water is going to go, and then another model computes the flood probability and so forth. But those files, or I'm sorry, those chained together models used the two-dimensionality of the planet to sort of simplify the inter-model communication. But you've said that's not the job of the connections. It's not the job of the tool, it's the job of the modeler to make those connections, right? By APIs and drivers, I guess.
Exactly, yes, yeah.
So doesn't that suggest that we should standardize those somehow a little bit? Otherwise people will be making all kinds of connections, right? I mean, and doesn't that suggest that you need to hold a convention to bring modelers together so that you can explore what the APIs ought to look like in general? Would that not be reasonable?
So what we experienced by modeling this hazard is that actually a lot of tools using standardized spatial data and for data, shape files, raster data.
Right.
Those are specialized more like what's independent. It's more like the config files, how they configure their models. I guess it would be good to have a standard, a unique one. So everyone can model. I think there are already some out there,
Sure.
but no one is using them because it's more work to look the standard up, and you never knows.
Well, that's right. That's why it's an impediment, I think. And
the idea also would be, as I said before, but this is how we say in German, Zukunftsmusik. So for the future, plan for the future is that you bring this more like to a community to make it open source, and people who are interested in this to say, oh, I work on rainfall data. I can easily write this API, put it up, and therefore I can use the soil data colleague of mine wrote or so like this. So it's more like having a marketplace to do this. And there are tools out there which are doing this, but it's more from the architecture community. Maybe some of you know there is this Dynamo from Archicad where you have the same philosophy. So there's a marketplace where people have a smart idea and then they upload the model, and then you suddenly can make octagonal roofs or something like that on your building, and you only have to load in their plugin. And so this would be, I guess, an idea for future, since providing this.
And my last question, I guess I didn't make room for anybody else's, about uncertainty and variability. Obviously, the rainfall events are stochastic, and I saw that you had many scenarios, but do you do them stochastic? I mean, do you do like a Monte Carlo loop in there, or no?
Yeah. So this.
That was a yes.
Yes. Yeah. So what this was more really like brute force Monte Carlo simulations, and there are much more smarter ways to do this for sure. And it was more like way to show that this is one possibility. And how we did the rainfall is we had similar to earthquakes. We had a list of previous rainfalls, and then we maybe randomized out of those previous events.
Right.
And something applied it to this area.
And do you have the rest of the answer to the question about uncertainty has to deal with the epistemic uncertainty and also how you handle dependence among the outputs. I mean, I think the limitation in the past with linking together models was never the complexity of the problem. It was always the complexity of the answers. So, the models take a whole bunch of inputs from different sources, from different layers, and then weave them together in these complex ways. And each scenario that comes out is a possible future. And the collection of such scenarios is the future in some sense, but they embody dependencies. One bridge goes out is not independent of the other bridge going out.
Yeah, exactly. Yeah, yes.
And that dependency is sort of embedded only in the collection of answers. So how do you handle that? You just store all the possible answers, and then access them later, or is everything in one scenario through all the models and the?
So what we have done here is one scenario was more like one future trajectory. So we started rolling the dice, and then we had a certain rainfall pattern, and we rolled the dice, and we had a certain roughness coefficient, and so on and so forth, till we ended up with.
Okay, so each scenario goes through the entire chain of models.
Exactly. Yes. Yeah.
Okay.
There might also be ways to do this smarter, and this is also, I guess, a way how we can reduce simulation time and cost. To think about this in a smarter way, not only having this one trajectory for one simulation, but maybe there are some common knowledge where we can use this, and we can start then with another.
Well, if you do it the other way, to have distributional answers rather than single.
Yeah, exactly. Yeah,
answers, then you have the dependency problem. You have to keep track of that dependency from time to time. And so, what do you do about epistemic uncertainty, where you have an interval rather than points, or do you not handle that?
No, it's also when it's not in the model itself, you can give them. So what you can specify is more like the input, which can be random, and the output. Now you give them, but so there is nothing here. So when it's in the model, it's up to the model regarding this.
Ah, okay. So okay. So can the output be intervals and an interval of answers then? Theoretically, it could if the API supports it, right?
Yes.
Okay.
It's actually implemented in, I think, in the damage functions. They don't give out one value; they give out a range, more or less. I think it was implemented, but I have to look it up. I think this was how the damage was implemented.
Okay, cool. Thank you. Thank you. I like this talk very much.
Thank you, Scott. Is there any further questions at all? Okay, if there's no more questions, I think we can probably wrap that up. Yeah, thank you, Jürgen, for giving a talk. I guess this ends the formal part. We can stop recording. Yeah. There are probably a quick couple of announcements we can make just before everyone leaves. And that is, we've got another talk. We have two talks of interest next Wednesday. One by Ryan Martin on false confidence, imprecise probability, and valid statistical inference. And one at 4 o'clock, so right after, which is hosted, organized by the BAME LGBT and diversity networks, which is talking about racism in academia and science. Yeah, otherwise, yeah, thank you, Jürgen.
Yeah, thank you very much.
Thanks very much. Thanks, Jürgen.
If any other questions arise, I'm available.
Yeah.
So please contact me. We can have a chat one-to-one, more or less.
Simon.
Hello.
Yeah. Do we need to register for the second event next week?
Yeah, so there's been an email sent around university, and we also forwarded an email around, and you need to register to be able to attend and submit questions.
Okay, cool. Thanks.
Thanks, everyone. Bye.
Bye.
Thank you.